Let's try to solve this question over here. A vessel contains an ideal polyatomic gas at temperature of 30 degrees Celsius. So you see that it's ideal polyatomic gas, so we know that the degree of freedom will be equals to 6 for polyatomic gas. Then we see that it's at the temperature of 30 degrees Celsius initially. Okay, so the temperature initially is 30 degrees Celsius. We know that we are doing anything in chapter 9 here, the degree Celsius must be converted into Kelvin. So let's just immediately change it to Kelvin, 273.15. Then it can be converted to Kelvin. This is 303.15 Kelvin. Okay, so at this situation, the total translational kinetic energy of the gas molecules is 6.00 times 10 to the power negative 6 joule. So this is total translational kinetic energy. So besides writing KTR, you have to write total as well. Because if you write KTR only is for one single gas molecule, if you include the word total, then it includes all the gas molecules in the system. Then it becomes the translational kinetic energy of the whole system, also known as total translational kinetic energy. So at this temperature, the total translational kinetic energy is 6.00 times 10 to the power of negative 6 joule. Okay, after that, more gases of the same kind is then added into the vessel that the mass of the gas double. Okay, so you add in more gas of the same kind. So let's just write add more gas of the same kind. Okay, so of the same kind means by your mass of one molecule won't change, your molar mass won't change, because let's say if it's ammonia, then it will continue to add ammonia, then will suddenly add carbon dioxide or something. Okay, it's the same ideal polyatomic gas being added, but now after this addition, you see that the mass of the gas doubled. So you can say that the mass of the gas doubled. The new mass of gas, you call it as m prime, but if you just write as m prime is equals to 2m, then you're definitely wrong. For small m here represent mass of one single molecule, but you're talking about the mass of the gas double. It's previously you have 1 kg of gas, but add on another 1 more kg of gas, so the gas total mass become 2 kg. That represent the whole system. If you represent the whole system, you should not use one single small m, because that means the mass of one single molecule. No, we are supposed to say the mass of the whole system. So we have to specify clearly the mass of the system nu is equals to 2 times of the mass of the system whole. Okay, just in case I'm obstructing, it's mass m subscript system. Okay, the mass of the system nu is equals to 2 times of the mass system whole. Okay, then the total translational kinetic energy of the molecules becomes 13.00 times 10 to the power negative 6 joule. So right now the new KTR total, which is new, right now it will be equals to 13.00 times 10 to the power of negative 6 joule. Okay, so some transition have happened, causes the total translation kinetic energy to change. Okay, so now they ask you to determine the new temperature of the gas and the change in internal energy of the gas. I believe if you look at this situation here, you can see there's an old situation and a new situation. So we are going to solve this as a ratio question. So if we solve this using a ratio question step method, then the first step will be to determine the relationship between the manipulated variable and the responding variable. The relationship between the manipulated variable and also the responding variable. So in this case, what are we manipulating? We are adding gas, right? So adding gas, we are manipulating the mass of a system. So the mass of a system is being manipulated. Well, actually, if you know that the mass of a system is being manipulated, you know that the number of mole of the system will also change as well. Because previously you have 1 mole of gas, then it becomes 2 mole of gas, only the mass of the system will increase, right? Okay, so if the mass of a system increases, the number of moles should also increase as well. If you need a mathematical proof, then you know that the number of moles is just the mass of the system divided by the molar mass, right? Okay, so if you increase the mass of a system, then definitely your number of moles should increase as well, because your molar mass will not change, because you're adding the mass of you're adding molecules of the same kind. You're not adding nitrogen gas, you're not adding helium gas or what. You're adding the same kind of polyatomic gas as just now, so the molar mass should not change. So if the molar mass doesn't change, the mass of the system increase, the number of moles should also increase as well. Okay, so that's just something to know. Then you know that if the number of mole increase directly, it also means that the number of molecules should also increase. Okay, the more number of mole you have in the system, the more molecules you have in the system. You can think of it as the number of molecules is equals to the number of mole multiplied by the Avogadro constant. So in this case, if your number of mole increase and your Avogadro number is a constant, so therefore it causes your number of molecules to increase as well. So these are the things that we are manipulating. We are manipulating the mass of a system by increasing the number of gas molecules inside to increase the number of mole inside the system. But what is the responding variable? What do we observe? Well, we observe the translational kinetic energy changes from 6 times 10 to the power negative 6 joule to 13 times 10 to the power negative 6 joule. So what has changed is the KTR total. Okay, they didn't mention that you change the temperature. It stays, previously it was at 30 degrees Celsius, but they didn't mention any change in temperature. Oh yes, there is. Question A asks for the new temperature of the gas. So later we need to figure out what's the new temperature. So temperature is definitely something that we observe as well. It's something that responds to the change of the mass of system. Okay, so this is our manipulated variable. This is our responding variable. So what do we do now? We need to find an equation that relates between all these things together. You have KTR total and you have your temperature. Well, if you look at your rectangle, right, okay, the rectangle consists of pressure, connects to KTR, connects to temperature, connects to VRMS. Okay, looking at this rectangle, we know that we are going to involve KTR and temperature. So KTR and temperature is on this side. So our equation will be found on this side of the rectangle, in which we have two equations. One is KTR total is equals to 3 over 2 nRT, or 3 over 2 nKT, or 3 over 2 PV. Okay, whereas the KTR can be equals to just 3 over 2 KT. Okay, so if we want to involve KTR total and also temperature, then we take the KTR total equation. Then any equation that has temperature inside would be good enough. So I think I will take the second equation, 3 over 2 nKT maybe. So from this analysis, I see that in order to include everything inside, I'll be using KTR total is equals to 3 over 2 nKT. This is the equation I picked from step 1. Then once I'm done with step 1, what do? I find the relationship between the old terms and the new terms. Okay, relationship between the old terms and the new terms. Okay, there are different ways to do this question. Some students, they will see that because the question asks for temperature, they are going to shift the temperature to become the subject. So if I shift the temperature to become the subject, then it becomes 2 over 3 KTR total divided by N and K. Okay, so 3 nK divided by 2. Okay, so this is the equation. If we shift things around, then make the temperature as our subject over here. Okay, so these are the things that might have changed. So let's find the relationship between the new and the old one. We see that KTR total for new, we know for sure is 13.00 times 10 to the power negative 6 joule, whereas the KTR of the old one, KTR total of the old one is 6.00 times 10 to the power negative 6 joule. Okay, so that's the first term that we derive the relationship between old and new. We just know the numbers. Then we have N and K. K is a constant. K is Boltzmann constant, is fixed, 1.38 times 10 to the power negative 3, cannot change. But for your number of gas molecules, you know that your number of gas molecules should be equals to how many times the old number of molecules? You know that your mass of your system doubled. Your mass of your system doubled. Based on this equation, if you double the mass, you double the number of mole. Okay, if you double the number of mole, this one is the Avogadro number is constant, you double your number of gas molecules. Okay, so mass double causes the number of mole to double, causes number of gas molecules to double. So this is 2 times of the old N. Okay, because the number of molecules doubled, therefore the mass of the system will double as well. Okay, so once you determine the relationship between old and new, what's the last step? The last step will be to take the new value and new equation, divide by the old equation. So the new equation, you have T, you have 2 over 3 KTR total divided by NK, but because it's new, everything deserves a prime. So we are going to add prime for the N, add prime for KTR total, add prime for temperature. Then I'm going to divide by the old version of the equation, so everything without prime. So 2 over 3 KTR total divided by NK. Okay, now we have reached this step. You know that what can be crossed out? Anything that is constant or the same can be crossed out. So K can be crossed out. That's what we can do. 2 over 3 can be crossed out. That's what we can do. Okay, so now we can further simplify the equation or substitute in the equation. Both are fine. So you know that KTR total new is 13.0 times 10 to the power negative 6 divide by the new n. The new n is just equals to 2n divide by KTR total. The old KTR total is 6.00 times 10 to the power negative 6. Then divide by n. The n is the old n, so this one you can cross out the n. Then from here you can do your calculation, and I believe that if you do your calculation, you'll get an answer which is 13 over 12. So we know that the new temperature divided by the old temperature is equal to 13 over 12. So T new is equal to 13 over 12 T old. So if you know the temperature of T old is the previous temperature, which is 30 degrees Celsius, 303.15. When 303.15, you are able to find the new temperature, and the new temperature should be 328.41. So this is how you obtain the new temperature of the gas. Okay, so again, it goes through the same three process: relationship between the manipulated variable and responding variable. Then you find the relationship between the old and new quantities such as KTR total, N, and also KTR total and N. Then after that, you take the new equation, divide by the old equation, cross out anything that are the same, sub in any values that you know are different. Then from there, you do further cross out to find the relationship between old and new. Then from there, you find the new temperature. Okay, so now let's move on to question B. Question B asks for the change in the internal energy of the gas. So if you ask for the change in the internal energy, probably you need a new page maybe. Let's write here as question A, then I'll continue with question B. Question B asks for the change in internal energy of the gas. So we know that change in internal energy is delta U. Okay, or in other words, you can write it as U final minus U initial. So you learn from the concept videos that the internal energy can be determined using the degree of freedom divided by 2 nRT or NKT, whichever you prefer. Okay, so you can write NKT, let's say, minus F over 2 NKT. Let's write it like this first. Okay, you are aware that during this change from the initial situation to the final situation, what has changed? You know that the temperature has changed from T initial, which is over here, to T final. The temperature has changed because you just determined the new temperature. Besides that, you know that the initial number of molecules has also doubled to become the final number of gas molecule. That's the initial number, but we are going to double it to become the final number for gas molecules. Okay, the rest, such as degree of freedom, we know that the degree of freedom doesn't change because you are adding the same polyatomic gas later, so the degree of freedom remains as 6. At the same time, you know that the Boltzmann constant is just Boltzmann constant. Don't need to worry too much about it, it's a constant. Okay, so if you choose to substitute the value, I believe you have some trouble because you don't have the number of gas molecules. But let's try to sub in the degree of freedom first, just to make things easier to see. Okay, you have your NFKTF minus 6 over 2 N initial KT initial. Okay, you definitely have your initial and final temperature. You can substitute that in. You also know your Boltzmann constant. You can substitute that in. But the problem is you don't have the initial number of gas molecule and the final number of gas molecule. Okay, it will be a bit complicated if you want to do it. If you want to find the relationship between initial and final, then use all the ratio thing. It'll be a bit complicated. But there's a smart way to go through it, which is to notice that this equation here, actually, it's equivalent to you taking 2 times 3 over 2 NF KTF minus 3 over 2 and initial KT initial. Okay, why do I factorize out a 2 over here and make it a 3 over 2 as our fraction? Because we know that if it's 3 over 2 here, what we have here is actually translational kinetic energy. Translational kinetic energy is 3 over 2 kT. If you multiply by the number of gas molecule, you get a total number, a total translational kinetic energy over here. So this is a total translational kinetic energy final. This is KTR total final minus what you have here is also 3 over 2 NKT. 3 over 2 NKT is again KTR total, but this is KTR total initial. Okay, so you have simplified the equation a little bit to become 2 times of KTR final minus 2 times of KTR total initial. So now this is 2 KTR total final. We know the value. KTR total final is 13.00 times 10 to the power negative 6. This is KTR total final. Let's put another bracket here. Then you are going to minus. Then you're going to put in KTR total initial. So KTR total initial is 6.00 times 10 to the power of negative 6. Okay, so now everything is clear. It's 2 times of final total translational kinetic energy minus initial translational kinetic energy. So it's a simple calculation, and I believe you get the answer of 1.4 times 10 to the power of negative 5 joule. Okay, so this is the faster way to solve this question by noticing that you can extract out the 2 over here to make it 3 over 2 NKT and 3 over 2 NKT. So in this case, you don't need to waste that time to find what is the number of gas molecule final, what is the number of gas molecule initial. All those things will, all the relationship thing can be simplified. We just change it to become KTR total final minus KTR total initial. Okay, so from there we determine the change in internal energy. And since it's positive, it means by your internal energy increases. So internal energy increases means by your temperature should increase. So if you look at the previous answer, you can see that the temperature is definitely higher than before over here. Okay, so everything sort of makes sense over here.